Okay, our first speaker today is Amie Norton from Kansas State University, who is talking about the detection of mercury in water using alfalfa nanoparticles. And so I'll let her take it from here.
Thank you very much. I'm excited today to talk about a new nanosensor we found that detects mercury in water. I'd like to start off by making some acknowledgments and thank you to the Kansas Water Institute. This project was funded by CoSearch, and also thanking my undergraduate who put together some of my graphics. So mercury is found in lakes. In all the states that are colored blue, they have at least mercury contamination in one of the lakes in these states. And so why we worry about mercury contamination is, of course, because of the health effects. And so it can cause deterioration of nervous system, impair your hearing and speech, and cause involuntary muscle movements. And what we're really worried about is the non-natural causes of mercury. And so mercury can be naturally occurring when volcanoes erupt. It's found in our Earth's core. But then we also have human causes of mercury, such as burning, coal burning, industrial causes, and industrial stream runoff. And so as we can see, there's a need to detect mercury contamination. And so right now, the way to detect mercury contamination involves cumbersome instrumentation, which involves a long turnaround. It takes a technical knowledge to read the data output. And so there's a gap in the knowledge where we want a rapid on-site detection. People have tried to fill that gap with gold nanoparticles, but these gold nanoparticles are not ecologically friendly. And so we have developed a sensor that's made out of nano alfalfa particles. Alfalfa is a common legume that is found on 6 continents. The amount of alfalfa in the cuvette that I'm going to show you later is less than 1 cent, so it's a cheap sensor. And upon exposure, the luminescence is going to turn from on to off. And so this is a graphic put together by my undergraduate, Audrey. And so the basic scheme here is that it's a rapid, environmentally friendly test. It takes 5 minutes. It's inexpensive. We've tested in different mediums, tap water, pond water, and milk. We can go from 2 to 80 ppm. And so this is how we make our alfalfa nanoparticles. We take the alfalfa and we ball mill them in ethanol, and we come up with an alfalfa particle solution. These alfalfa particles are luminescent under black light. We took a dynamic light scattering. We milled it in many different solutions. We did ethanol, DMF, hexanes. In the next slide, I'll show you the array of solvents we did it in. But the dynamic light scattering shows the size. That size array was broad, other than in ethanol, where we get a narrow size array. The dynamic light scattering shows that our particles are about 50 nanometers. We did a TEM of the particles, and they range from 122 nanometers to 205 nanometers. You may be wondering why our dynamic light scattering is different than our TEM. The reason why is sometimes when you dry out these particles, you can get some aggregation. Sorry. So one thing we did was we did UV vis and milling these particles in different solvents to see if there would be solvent changes to these particles. And we see that the particles themselves are the same in different solvents. There is a slight shift in the solvents, but overall the spectra is the same. We matched it with a chlorophyll spectra, and it matches. So we think we make the chlorophyll more readily available. So what we're looking at here is the UV vis of the chlorophyll on the alfalfa particles. You can calculate the species of chlorophyll that you have. So there's chlorophyll A, chlorophyll B, chlorophyll C. So we went through that calculation. And the interesting thing here is that mostly we make chlorophyll A and chlorophyll B in all solvent cases other than hexane, where we make more of that chlorophyll C species. We haven't really investigated that. I just point that out as a interesting factoid. So going forward, we really focused in on that ethanol because we made a narrow size range, and we really can control that size of the nanoparticles more than the other solvents. The other thing is that in water, you could see that our band in the UV vis was lower, and that's due to solubility issues. And so here we looked at the kinetics of the response in ethanol as we were milling. We stopped the mill at 15 seconds, and we went all the way to 30 minutes. And we can see that the reaction, we started making product at 15 seconds. And so we see an increase at this band at 685 nanometers. And here's what the kinetics look like. And so from 15 seconds to 5 minutes, our reaction is complete. So it's a very fast reaction. So we also took the emission and the excitation of the particles. And the excitation and the emission match that of chlorophyll. So we're just making sure that we confirm it's what we think it is. And we get a emission spectra of around 700 nanometers. We excited at 450, 500, and 550. So now we started to do our detection. So you can see the, I think it's your right, the cuvette on the right is the alfalfa particles in ethanol. Once we add that mercury to them, the luminescence disappears. So we did the emission spectra before and after adding mercury. You can see the emission spectra after 20 ppm of mercury totally disappears. We did a calibration curve from 2 to 80 ppm of mercury, and we can tell how much mercury is in that cuvette of how much mercury is in that sample. We wanted to look at more complex mediums. So we looked at milk, tap water, and pond water, and the solid lines are without mercury, and then the dotted lines are with mercury. And you can see in all samples, after we put in 20 ppm of mercury, we decrease the UV vis. So we successfully synthesized and characterized a new alfalfa nanoparticle. We determined the rate of the reaction. We developed a biodegradable colorimetric sensor, and this sensor is eco-friendly. How much time do I have? We have 5 minutes. I can take questions now if there's any.
On that last slide, it looked like the milk went from the top line, and then when you added the nanoparticle, it went to the bottom line. Do you know why that is?
So both of them have the nanoparticles in them.
Oh.
It's when we add the mercury in. So we totally quench that signal. So in milk, it totally quenches out the signal. And I think it's because we're conjugating, milk is really complex, and we're really changing the particles after we add the milk. But we still get the same effect of losing that luminescence.
Thanks.
But it is a different signal than in water. But you still lose the luminescence. So it still works, but the mechanism might be different, which is interesting.
And I have a question that really isn't even related to the milk. What would it take to bring this to market so that people could test their water using the alfalfa particles?
So I think that what we'd have to do is get at the EPA level, which we need to get down 10 times, I think. Right now, we're just with the complex, which is, it's good sensing with the complex we're this low. To get it farther down, I saw that if you put it on something that's more basic, like a basic, someone did peanut shells with chlorophyll and they brought it down quite a bit. So if you put it on some kind of medium that people can actually put into their water, I think that might be the trick that somebody can actually sprinkle in. And then you would have to get a company that was interested in it. I presented this somewhere else and someone asked, can you do cadmium instead? Because cadmium is a big problem in food and it might be of more interest if it's cadmium. So I haven't tested cadmium. So,
Thank you.
Other questions? And just a quick, it's really interesting. Is this something that would be like, durable? So if it was a product, would it be like shelf stable, or are there requirements for storage that would be challenging?
it's, sorry, it's shelf stable in solution. So as long as you keep it in solution, you're okay. As soon as you start drying it out, you start changing the particles. And that might be challenging. A company might not want a solution that they have to ship, but it's a safe solution. So it might not be an issue. I'm not sure.
Yeah, no, I have same question, but also, what's the minimum? I mean, this is, but what's the minimum level of mercury you could detect?
We can detect 2 ppms right now.
And how much? Sorry for. How is that not for? I honestly don't know that much.
So 1 ppm is like a drop of water in a fish tank, a 20-gallon fish tank. So it's a low amount, but it's not at EPA level. To go the EPA level, I think we have to be at 1 part per billion. So we have to drop it another level. It's an interesting proof of concept right now, but there's other things you can do to manipulate it to get it down to that level.